NanoHub U, online instruction.
Hi everyone, welcome to lecture 211. In the last lecture we were talking about how to use the graphical user interface for S4, which is located on NanoHub, known as S4 Sim. And now we're actually going to say, based on the input parameters that we specified, what kind of outputs can we get? So here's kind of an example of what the output window would look like. This is showing like a reflection spectrum. And you can see that there's an x-axis, which is the wavelength, in this case in nanometers. And so we would see the reflection is kind of experiencing a very large dip in a certain range of wavelengths, which is maybe in the blue in this particular case. And we actually have several different lines in this line graph, and we can selectively add or subtract these different lines depending on our needs. And the second feature that may be of use or interest is that in addition to the graphs that we're outputting, which can be customized, then we can also take the control file that was used to run S4, and then we can customize that. Basically, by taking the auto-generated control file and making any changes that aren't explicitly available through the graphical user interface, and then we can run it back into the graphical user interface system by just directly providing a control file. So that means that we don't necessarily have to become experts on Lua in order to use the more advanced Lua features in this context. And then another thing that may be of interest to some users is that we actually get a whole bunch of raw output, which we all select using this drop-down box at the top of the output screen. And this raw output data basically is the log file of what S4 produces when we run it. And so this raw data may be useful if you need to replot the data or otherwise process it in your own software, like say MATLAB. Now I'm going to give you a specific example of how S4 can be used to provide accurate simulations that correspond to what's seen in literature. So in this particular case, we're looking at the front coatings for silicon photovoltaics. And so you may or may not know that for silicon photovoltaics, typically you would add a single anti-reflection coating, oftentimes made out of silicon nitride. And so that gives us like a certain value given the refractive index and the thickness of the silicon. And so however, you can actually get improved performance if you add more layers beyond that initial first layer. And it really depends actually on the silicon thickness itself, like what is the best front coating design and the set of refractive indices and thicknesses that would be most suitable. So this is kind of showing a chart from like paper a few years ago, which shows like as a number of the front coating layers, like what the real and imaginary epsilon is, as well as what are all the thicknesses. Okay, and so then we can actually take those values that were calculated in that paper, which you can see here is cited here. And this was the graph that was in the paper, kind of showing like what is the absorption spectrum of these optimized structures, like for either zero front coating, which of course has the worst absorption. So this is just a bare silicon wafer. One front coating, which like I said, is kind of the industry standard. And then what if you add 2 or 3, that's in red and green respectively. You can see that you get like better response a little bit here in the longer wavelengths, but especially in the shorter wavelengths, you get much better response, like greater absorption. And then similarly in S4, you can actually run that exact same simulation. You can see that if you graph it in the same way, then the results are very close to the point that the only way to really distinguish these is just the thickness of the lines, but otherwise the results are essentially identical. So this kind of validates the method to show that this highly accurate approach to solving these sort of problems. And just to show you a few more examples, you can see output of S4Sim when you have a multi-layer stack has like these oscillations. These are known as Fabry-Perot oscillations, similar to what was seen earlier as sharp spikes. And then these are spread more gradually because the thicknesses are smaller. And so these Fabry-Perot oscillations were also expected analytically. And then if you have like a slightly different kind of structure, which is a 1D square grating made out of silicon and air, then you can actually calculate the transmission. And this also has like a pair of dips in transmission, which were also seen in previous literature. And then finally, there's this other structure that was in this Tikhodev paper that was one of the foundational papers establishing the S-matrix method with periodicity from 2002, and you get a good match with one of his graphs, figure number 4, which shows basically a very sharp transmission spike in this more complex structure. So in conclusion, S4Sim has been highly validated and shown to match with a lot of the literature calculations for multi-layered structures. In the next lecture, we'll talk in more detail about what are some other tools that are based on S-matrix method.